This is the first segment in a topic that will cover how to create databases, including declaring database tables and columns, the choices of column type, declarations of various key types, and good database design in general, including an informal discussion of normalization. Now, to start with, let's talk about DDL. SQL includes a subset of commands called DDL for Data Definition Language. And these involve defining databases, setting up tables, columns, keys, and so forth. Our bakery2.sql file, up on screen here, is filled with such commands, and we'll use it as an example in the following discussion. For instance, near the top of that file is a block of statements for create statements to create the bakery2 database, and then the tables within it. And we'll go over the create statement in more detail shortly. Inside the create table statements, we can see column declarations that include the type of the column, for instance, int or varchar. We touched lightly on the issue of column types earlier when we looked at the show columns statement, and we'll go over column types a lot more in this topic. Any programming language has variables that contain data. SQL's equivalent is the column, and variables, or database columns, have types, specifications as to what type of data they store, for instance, integers or floating point numbers with fractional parts, strings of characters such as names, dates and times, and so forth. SQL offers a pretty powerful set of column type choices, more so in fact than most programming languages. And so, an obvious question then why would a database language have such fine type distinctions? There are three major reasons that we should look at here. First, as we'll see in the lectures to follow, many type choices involve a trade-off between the amount of disk space a column takes and the flexibility or range of the data that can be stored in the column. Disk is cheap, but databases are large, and a table may have millions or even billions of rows. Even the saving of 1 byte in a column results in reduction of data size by as much as a gigabyte when you've got lots of rows. Range and size trade-offs are important when a column appears in millions or billions of rows. The second is that database design focuses heavily on detecting and preventing human error. Much of the data in a database is provided directly by humans rather than computed or programmatically generated. For instance, we'll see that SQL offers an unsigned integer column type that forbids negative values. Precluding negative values makes storing an integer on disk a bit more efficient, but the real purpose of unsigned integers is not efficiency, it's preventing human error. If the column in question holds a person's age or weight, or a count of students in a course, or a number of items purchased in a receipt, then clearly a negative value is wrong. An unsigned integer prevents accidental entry of incorrect negative values. Then third, disk data storage benefits from predictable size of columns, especially for variable sized data like strings. So SQL offers subtle column type variations for declaring variable sized data and for giving hints as to the expected size of such data. While we're at it, another good example of SQL's error prevention is that it won't let you leave a column uninitialized. Every column in every row must have some predictable value, even if it's automatically assigned. Uninitialized data is the bane of languages like C, since it produces unpredictable, often hidden bugs. When we learn the SQL insert into statement that adds new rows to a table, we'll see that leaving a column uninitialized results in an error unless you've otherwise arranged for it to have a value. And see below for how to otherwise arrange a value. We'll be talking about that. So these three themes of size and range trade-off, preventing human error, and making column sizes as predictable as possible will recur throughout our column type discussion. Now, by the way, also, some of the column types we'll discuss are standard to all SQL compliant databases. But the standard SQL types are a bit limited, so every DBMS offers non-standard additional types. And these are pretty similar across all DBMSs, but the type names and rules for each are a little different. We'll point out those types that are SQL standard, and you may assume any types not identified as SQL standard are MySQL types, but they'll be very similar to types you'll find in other database management systems. And then one final item before we start looking at the DDL directly on the slide here. We discussed keys in the prior topic, and we used both primary and foreign keys in our queries. In this section, we'll look at how you declare a column to be a key, including a primary or foreign key. This includes, there's a brief example right there, for instance, in the file. This includes arranging for automatic incrementing of primary keys with each new table row, and enforcing strictly the rule that a foreign key in one table must have a value that matches a key value from another table. So, that's the overview. Now let's look at some specifics. The most important DDL command is create, or all caps create, since SQL keywords are not case sensitive. Create may be followed by various modifiers to create different things. For instance, create database or create table, and so forth. The create statements at the top of Bakery 2 SQL are good examples. Preceding these, by the way, are is a drop database statement mentioned in earlier lectures. This drops any existing Bakery 2 database and its tables if they exist, and it clears the way for creation of a fresh Bakery 2 database. Now, the create database Bakery 2 statement on line 2 here creates an empty database called Bakery 2 with no tables. But even this simplest of create statements has a few options. And per usual, I'll ask you to augment the lecture content with a bit of research in the documentation, with the intent of making the documentation a familiar tool. And so question 1. At least look briefly at the options for create database, in particular the create specification in the MySQL docs. What do the options appear to be for, generally speaking, and when might they matter? And if you look at the docs, what you'll find is that the create database options let you specify something called a default character set used by the new database. Databases may store strings from many different languages, which means that ASCII characters may not be sufficient. There's a myriad of character set choices available, including several different ways to store Unicode characters. And the options even let you specify the collation order, which is the order in which characters are sorted, which matters for string columns. And this actually differs from culture to culture. In effect, everyone sings a different alphabet song and has a different ordering of the letters, especially since they usually have different letters from English as well. Now, you don't need to know the details of these features right now, but at least be aware of the issue of character set and collation order in string columns, especially if you're designing a database for international use, for instance, for an international website. Okay, so on to create table here. Once you have a database, you can use the create table statement to add tables to it. On line 3, note we do a use Bakery 2 command, which, as you know, means that all following commands are in reference to Bakery 2. So after this are all the create table statements, and all of them will create tables within Bakery 2. You can see each create table statement takes the form of a create table and name header, followed by a parenthesized list, the parens there, of comma separated column declarations. And there are also, by the way, constraint declarations like this primary key line, and then there's a foreign key and unique in various places. We'll get to those a little later. Now, it's nice style to put the declarations on separate lines, as we do in Bakery 2 SQL, but it's not required. DML, like all of SQL, is free form and treats line breaks like any other white space. How you arrange lines and indentation is up to you. And note that the column declaration list is enclosed, as I emphasized, in parentheses, not curly braces. SQL consistently uses parentheses where many languages would use curly braces, and the error messages you get from a mistaken use of curly brace are often baffling. So remember that it's parentheses, in other words. This is more 1970s language design, by the way. The use of curly braces to group things in programming languages became common after SQL was standardized. And then question 2. Do a bit of reference research on the create table syntax and tell me how you'd create a table whose columns are exactly like those of another table without repeating all the other table's column declarations. And the answer then is that the like option does this. Create table, new table, like old table. That makes new table a duplicate of old table. So now let's look at column declarations. Each column declaration in create table takes the form of a column name followed by a column type and then optional qualifying terms. We'll look at all the types in detail shortly, but given the earlier no uninitialized data discussion, a few of these qualifying terms deserve discussion now. One way you can otherwise arrange for a column to have a value is by declaring a default value for the column, as we do in Bakery 2 for various columns. And a good example is line num in line item, which has a default value of 1. Any column declaration may have a default modifier followed by a default value. If no other value for that column is provided, the default gets used. This is especially useful when adding a new column to an existing database table, as we'll see in a later topic on modifying databases. In line num's case, this means that line num will be 1 if we don't specify otherwise. Now, many of the default declarations in Bakery 2 specify a default of null, like these here. A null value is a way of saying we have no value for this column, but it's a predictable, testable value. It's not uninitialized garbage. By default, all columns allow null values and are thus said to be nullable. Columns that must have a non-null value may be so declared by the option not null, like that, which makes them non-nullable, requiring some meaningful data. For instance, all of Bakery 2's primary and foreign key columns are not null, non-nullable, since it makes no sense, for instance, to have a receipt record with no linked customer row. And certain critical non-key data, like the customer's last name here, are also non-nullable. But Bakery 2 permits null values for many less important columns. For instance, the flavor of a product or the purchase date of a receipt. Now, some products might not have a flavor. Perhaps some receipts might be non-dated. And almost all of these columns also have a default value of null. So question 3 here. Based on what we just discussed, is product price nullable or not? And are we required to give it an explicit value when creating a new product row? Think a little carefully on this. Price, in fact, is nullable. Remember that the absence of a not null modifier makes it nullable, since nullability is automatic, like we said earlier, unless you indicate otherwise. There is no need to specify a default of null or otherwise to make it nullable. But it has no default value, not even null. So we will have to assign an actual value, including possibly null, when creating a new product row. Now, comparison of null values follows special rules. If we use equal to compare two product prices and one of them is null, the comparison is false. No surprise there, but if both are null, the equal comparison is still false. And oddly, if we compare them with not equal, the result is also false. a null value is sort of a false machine. All standard comparisons involving a null are false. This makes more intuitive sense if you think of null as meaning unknown. If two prices are both unknown, we can't say they're equal or unequal. In effect, the introduction of null into any comparison makes the result uncertain. So SQL just returns false to be safe. And question 4. Okay, so then how do you test to see if a value is set to null or not set to null? If equal and not equal comparisons always return false, then what does work? Look up the special syntax for this. The answer, and I'll tap it up here as we go too, is you test a column for null content via the special comparisons is null or is not null. So where, for instance, price is not null. Literally, that's what you would type to check to see if price is null. Or price is null. That would return true if price contains null. And price is not null, of course, returns true if price contains any non-null value. And then a final note here. You probably noticed that all the table and column names are quoted. This is not required, but it is common SQL style, along with loud capitalized keywords. Whether you use these styles or not is up to you. The all caps is rather 1970s, and our SQL files only have it because they were generated by MySQL itself. The quoting of table and column names has a small advantage, quote unquote, in that it permits a table or column name to be a SQL keyword. You could actually create a table named select, for instance, and that will create a table with that name if it's quoted. But if it were not quoted, then it would merely generate the error that you actually deserve for giving such a name to a table. So again, it's really not an advantage per se, but that's one thing the quotes make different. And once again, the quotes only appear in our examples because they are MySQL generated. You don't have to use them. So in the next segment, we'll go over MySQL's many varied numerical column types.